All right, today we're going to look at and review definite integrals and what those are. A definite integral is said to be the sum of all the area under a curve. To do this, we're going to approximate it today, and look how you can approximate it with something called a Riemann sum. And what a Riemann sum does is it takes the amount of space you have under a curve and approximates it using rectangles. And so we're going to look at a graph and come up with what are those areas of those rectangles to approximate what the area under the curve is. When we're doing this, it's going to be the summation, that's the summation symbol, of the area of the rectangle. And you find the area of a rectangle by doing the width. In this case, our width is going to be our change in x here, how wide these are, times the height at each of these x of I. So x of I is the distance, the y value here. So the y value is f of this value. And so f of xi is going to be our height. So to find the area of a height, you take length times width. When you add all those rectangles up, you get an approximate area under the curve. Remember from last year, if your curve goes underneath the x-axis, that area comes out to be negative, since the height is going to be a negative number. And so then you get the net area with an integral, or Riemann sum. All right, so let's kind of just review. This one wants us to evaluate the graph of f of x equals x cubed minus 6x on the interval from 0 to 3 with 6 sub-intervals, taking sample points to be the right endpoints to approximate this. Okay, so first we got to figure out what's our change in x going to be? How wide are these going to be if we're going to use 6 sub-intervals on this interval? So our change in x is always going to be those two endpoints, A and B here. If we subtract them, that would give us a distance of 3 over how many of these subintervals you're doing. So here it's going to end up being 3 minus 0, or 3 divided by 6, or each of these rectangles should be 1/2 wide. Our heights of all these are going to be what the height is at these right endpoints. Here's a picture of what this looks like graphed out. So if you graph out x cubed minus 6x, you get this graph. All these rectangles now are going to be 1/2, 1/2, 1/2, and so on wide. Okay, and adding up half, 6 times gives us 3. So that works out. To find out how, or the height of these, then we're going to need to know where are we going to be taking the height from on the right side. Well, if we do this, this first one is going to be at 0.5. This will be at 1. This will be at 1.5. This will be at 2. This next one will be at 2.5. And here we can again see 3. If we're using right endpoints, that means if we draw this rectangle out here on the right side, that's going to be the height. We want to keep going till we hit the curve. That becomes the area we're finding. Again, at 1, keep going down till you hit the curve. That's that rectangle. Keep going down till you hit the curve. That's that one. Always using the right side. Here we're going up till we hit the curve, and then finally this one up till we hit the curve again on the right side. Those become our rectangles. So what are those heights? You can find those by just plugging in those values then into the function to figure out the y value or the height. So for example, at 0.5, if we plug 0.5 in for x, we should get that. So we're going to do 0.5 cubed minus 6 times 0.5, and whatever that equals, that's the height there. Probably the quicker way to do this would be to do calculator. So on the calculator, let's go in, type this function in. So we got x to the 3rd power minus 6x. Now if we go into our table settings, we want this going up by not 1 but 0.5 here, 1/2. And now if we go to our table, we should be able to get all these. I also need to adjust my table settings here. I want my independent variable back to auto here. So now it should come up with all those values here. So our heights are going to be all these values at 0.5. If we evaluate this out, it's going to come out to be negative 2.875. And if we do those other values, we can find those as well. So at the height at 1 is going to come out to be negative 5. If we plug in some of these other ones, we're going to want to scroll down here. We can see these other ones that we need. So at 1.5, it's negative 5.625. At negative, or at 2, it's negative 4. Now this next one we know should be positive here because it's above the x-axis, and we do get a positive value here at 2.5. It's 0.625. And finally, our last one here, the height at 3 ends up being 9. So those would be all the heights that we want to use. So now when we're setting up this Riemann sum to figure this out, I'll use R for right endpoints, and I'll use a subscript of 6 since we're doing 6 subintervals. It would be the summation of all those areas of the rectangles. Remember, area of a rectangle, it's going to be half times the height at all these. So we'd be doing 1/2 times the height at 0.5 plus 1/2 times the height at 1 plus, and we're going to keep doing that all the way over till we get to 1/2 the height at 2.5, and finally half times the height at 3. Okay, now you notice in this case, this won't always happen, but since we are splitting this equally, they all have a half in there. We could, to speed this up, and so we don't have to keep multiplying each one by half, factor it out, and then just come up with those heights. So those heights, again, would be all those points we had that we came up. This one was negative 2.875 plus negative 5 plus negative 5.625. We're adding all these up. Negative 4 plus 0.625, and finally the last one was a height of 9. So now we want to add all those up, times by half. That's going to give us an approximation of this area. I've entered this in on the calculator over here and calculated it out. It ends up being that our approximation of the net area then is negative 3.9375. So that's an approximation of the net area. It is going to be negative here because most of our area does occur below the x-axis compared to just the little positive part on the right. We could repeat this process with more rectangles to get a more accurate estimate. So if we used 40 as our number of rectangles, this would is what the area would come out to be. If you used 100, you'd get this. If you used 5,000, and you can start seeing you get a more accurate estimate here. Ours was pretty low because we only used 6, but the more you would use, the better approximation you would get. If you were to do it with left endpoints, not much changes, especially because this is still 6 subintervals. We would still set up this up as half being all ours, except now instead of starting with half, our first rectangle, if we use the left side height, would be actually 0, because that's our point right on that is at 0. Our next rectangle using left endpoints would look like that. The next one would be that, so you can see these are become a little bit different here. If we use the left side each time, some of these rectangles are now changing. So if we use all those green ones, that would give the left side estimate. So you would start with f at 0 and add all these up, still going by 0.5, except now your last one would be using f of 2.5 instead of f of 3. You would calculate it out the same way. We could again factor out half because they all got half as the width, and you could add up these heights. It'd be a lot of the same numbers here that we used before. Just now this would be, now we would just stop without using that height of 9 at the end. Our last one would be that height we had of 0.0625. I'm not going to calculate this one out, but it would give you another estimation. This one would probably be a little bit more negative, and then if you had those two estimates, we'd know it'd be somewhere in between those. A third way you can estimate with Riemann sums is using midpoints. If you use midpoints, you're still going to use the same change in x, except that you're going to calculate your height from the middle of each rectangle. If you want to find the middle of something, then what you do in anything is you find basically the average. So if you're finding the average of two things, add both things up. So you're going to add up both endpoints and divide by 2, or take half. So if you add up the endpoints on either side and take half, you would get the midpoint height. Let's show you that on this one. They want us to find a Riemann sum for the function 1 over x from 1 to 2 with 5 subintervals, taking the sample points to be midpoints. Okay, so let's find our change in x here, how big each rectangle would be. That's our A, that's our B. So we got 2 minus 1 divided by, here we're using 5 subintervals, so each one is going to be 1/5 wide. For midpoints then, we're going to take the height to be the midpoint of each. So if we look at what this picture looks like here, all of these are going up by 1/5. So this would be at like 1.2, 1.4, this line's at 1.4, 1.6 would be this line, 1.8 would be this line, and then we get to 2. But if we're going to use the midpoint height, then we'd want to take it in between. So we'd want to find what's the average of 1 and 1.2. If you add those up and divide by 2, that's going to give you 1.1. So we'd actually use 1.1 as our height, or function at that height. This would end up being 1.3. 1.5, everything in between. And if you notice from the picture, this is going to give us a little bit better of an estimate, because yeah, we're a little bit under right there, but we also go a little bit over. So that should give a pretty decent approximation actually of that height. Because if you just think about, if we had this little bit of height, actually right there kind of fills it in. Same thing as we go down here. So midpoint usually kind of gives you a little bit better of an estimate. So how would this one go then? We would do this as a midpoint. I'm going to use m for midpoint 5. All the heights here would be 0.2, and now we would add up this at, we'd want to use the height at 1.1, 1.3, 1.5, 1.7, and finally 1.9. And then multiply that by 0.2 and you get it. We're not actually going to go through and do this, but it's more that you remember how to set these up. I think you guys know how to go through and calculate up. All right. I'm going to give you an example from an actual AP test here. This was a question on the AP test, or one of the AP tests, and you can see that one of these does have a Riemann sum with it. So I want to kind of show you one that had that. So this one says water's pumped into a tank at a rate indicated by this function W in liters per hour from 0 to 8, where T is measured in hours. Water is removed from the tank, modeled by R, liters per hour. R is decreasing on this. So here this table is showing you this function R where the water is being removed from the tank at this rate. From time equals 0 all the way up to time equals 8. There's 5,000 liters of water in the tank at time equals 0. Estimate the derivative of R at 2. Show the work that leads to your answer. Okay, so if we have the derivative of R here, that's derivative, member, is the rate of change. So they want to know what's the rate of change in this water leaving the tank at 2. Notice we don't have 2 hours up here. Two would be somewhere right in the middle there. So the best way to probably estimate this would be to use the two values right around 2 there to do that. Remember, derivative finds slope or rate of change, and so the best way to estimate part A here would be to do just a little slope formula here with rate of change. So subtract our y values, subtract the x values that go with that, and we find out if we subtract those, you get negative 240 over 2, and if you divide that, you get that 120 liters per hour is what R is in, but then this would be per liters per hour, basically per hour is how fast this would be leaving. And that's, so it's the rate of change of the rate of change is what we're looking at there. Part B, use a left Riemann sum with 4 subintervals indicated by the table to estimate the total amount of water removed from the tank during the 8 hours. Is this an overestimate or underestimate? Give your reasons. Okay, so here we do want to use one of those Riemann sums now. So if we're using a Riemann sum here, we want to be able to come up with an estimate of how much is being taken out. The consumption under this would be the number of liters. Since this is liters per hour, if we do an integral, it's going to give us just the number of liters there. All right, so we want to do a Riemann sum with 4 subintervals using left. So I'm going to put an L there so I remember it's left. And we want to do with 4 subintervals with what we're given up there. So what we know here, if we're using left subintervals, we'd want to use the very first point we hit there. So we're going to want to do what is the amount at 0 here. Okay, so at 0, if we're doing 4 intervals here, this would be, moving this. This would be an interval here that we could use. This would be another interval we could use. This would be a third interval we could use, and this would be the fourth one we could use. Now, if you notice, this one, the intervals are not the same. Like here, it goes up by 1. Here, it's going up by 2. Here, it's going up by 3. Here, it's going up by 2 again. So we don't, our change in x is not the same each time. So this one, you got to kind of think of what those, how wide those each of those rectangles would be. This first one has a width of 1, and then we're going to need to fill in the height. The next width is 2. We're going to need to fill in the height. The next width is 3. We're going to need to fill in the height. And the last one has a width of 2. Again, fill in the height. What heights do we want to use? If we're using the left one, then we want to use the one on the left here. If it had said right one, then we would use that one as the height. So if we're just looking at this rectangle right here, this would be the left height. So this first one would be 1340. On our next rectangle, that would include these two. Now that would be the height, because that's the left one. If it was the right one, again, we'd use that one. And if you keep going here, the next rectangle that includes these two, this would be the height, so 950. And finally, the last one, if you did the left one, that would be 740. So now if you go through and calculate that out and find all these rectangles and add them up, that would give you an estimate of the number of, or amount of water that left this during those 8 hours. Just to save time, I've already kind of went through and calculated this out. You're going to get an estimate that 8,050 liters left or was removed from the tank during those 8 hours. The other part of this question, they want to know, is this an underestimate or overestimate of it? To get this, you have to see, okay, if we go back up, is the water leaving or going in? Well, we know it's leaving because it says it's decreasing. So if we got a decreasing function and we are using left endpoints when doing these rectangles here. So I'll just draw on a couple sample ones here. If we're using left endpoints and we have a decreasing function, is this going to be an overestimate or underestimate? You can see the amount of area here is over what it should be underneath that graph. So this would be overestimate. So we'd say overestimate because it's a decreasing function and we're using left endpoints. And that would be a good enough explanation to get full credit on that one. So that's an example of a problem that uses endpoints. The other questions we're gonna leave for now because we haven't quite reviewed some of the other material. Okay. On this next part, we start looking about at the actual like integral notation. So integral notation again, you got the integral sign here. It kind of looks like an S because it stands for sum. That's why it kind of looks like that. Here's your upper limit right here for B. That's where we're ending. Our lower limit's where we're starting. Our function that we're taking the area under goes here. And then dx kind of represents our variable of integration. Where that came from is this same limit notation that we had looked at before with a Riemann sum. So if we have that Riemann sum of all those heights and widths, and we have however many number of rectangles, if that number of rectangles goes towards infinity, then we would, in essence, all those infinite rectangles would give us the exact area of this area under the curve. So what you should be able to do is maybe jump back and forth between those if they gave you any questions. So here's an example. They want to know what would be the limit that would be equivalent to this integral shown. Okay, so you got to kind of know if our limit here, if we got to write out a limit, it would be the limit as the number of rectangles goes to infinity of the summation of all these rectangles from the first one to this nth one. And then we want to figure out, okay, what would be the height and width here that we're doing. Let's start with our width. Our width again is, remember, b minus a over n. So we'd have to look at this interval and figure out what's a, what's b, and so on. So here a would be 1, b would be 7. So we can come up with that change in x. Change in x would be 7 minus 1 over n, which would be 6 over n. So we know when we're writing this out, our change in x here would be 6 over n. So this is going to have a 6 over n in this summation. The other thing we got to find out is what would be this, what would be all those heights? Okay, what are those heights going to be? So that would be our function at x of I. X of I is our first point plus all these i's times the change in x. So to figure this one out, we are going to have to figure out what is that x of I. What's that? What's the distance that we can then find the height at with f? So we would take our a point, which is again 1, and onto that we're going to add the change here. The change would be I times our change in x, which we already found. Our change in x is 6n, 6 over n, so 6 over n. Or we could also write that as 1 plus 6i over n. Okay, but that's x of I. If we want the function at that, now we need to plug this into our function for x. So if we plug that into our function for x, with our function being 2 plus something cubed, the something we'd be putting in would be this. So if we want to write this out as a limit, it would be 6 over n times the square root of 2 plus 1 plus 6i over n cubed. This limit, if we calculate out, should give us the exact same value as if we would calculate out this integral here. It's just another way of writing it. We don't usually tend to use the limit way, but if you were to get a question on that and they want you to be able to jump back and forth, that's how you would do it. Again, it finds area under the curve. Integral finds area. If you increase the number of rectangles here to infinity, now these are so small you can barely see them, you get this smooth area under the curve. If you got area underneath, again, remember that comes out negative. So you get the net sum. You should be able to, on some of these, maybe not find them with an integral, but still be able to calculate it out. For example, this one, evaluate this integral. Even with some of the stuff from maybe from last year, this is a hard integral to actually calculate out. But if you were to graph this function right here, if you were to graph that, it looks like this. It's actually part of a circle. So even though we might not be able to calculate that out with some of the techniques you might remember, you should still be able to find this area, because if it's part of a circle here, we know area of a circle is pi r squared. For a whole circle, this being a quarter of the circle, then the area of that would be 1/4 pi r squared. The radius would be 1, and so the area of this would be pi over 4. So even though you might not be able to calculate some of these out, you might have to think geometrically on some of these in order to do that. Some of the properties of integrals from last year, if your limits are the same, you don't have basically any width then, so your area is going to be 0. If you're starting and ending in the same spot, there's no area to calculate out. If you switch the limits around, you get the same value but negative. So anytime the limits get changed around, you get the same value but negative. Constants, remember, can get pulled out. So if you have a constant, you can do that. But basically any constant one, it's going to come out to be area of a rectangle. That's why it's shown this way as b minus a. If you just have a constant function and you want the area underneath, the height is going to be c, and the width would be b minus a. So it's just going to come out to be a rectangle. If you're adding or subtracting functions, remember you can break those up into separate integrals, either being added or subtracted here if you're subtracting them. Constants, again, can get pulled out if it's with a function, and then you can multiply that back later. And then finally, this last one, if you have a function that starts at A, ends at C, and then another one that starts at C, ends at B, that would be the same as the function from A to B. This one kind of as a picture here would look like this one. You got a area from A to C here, plus the area from C to B would be this area, the second one here. That would just be the same then as saying the area from A to B and skipping that middle part and just making this in one. The key one with this one though, if you're using this property, you have to end, and then the next one has to start at the same value. If not, this property doesn't work. Here's an example of maybe one where you have to find some of this stuff. What would be the area on this one from 3 to 5? Remember, areas measured from under the curve, so they're looking at what is this area here. Well, this one looks like they tell you it's a semicircle here. So we could calculate out the area of these two squares, which we would know would be 2, and subtract the area of that circle, and what's left over should be the area we want. Area of that circle, or semicircle, would be half pi r squared, and the radius of that semicircle would be 1. And so this looks like we get 2 minus pi over 2 as the area. The other one here says what's the area from 6 to 10, but it's the absolute value of this function. Well, area from 6 to 10, that's all this area with all this area. If it had been just 6 to 10, those two triangles look the same, and remember that would end up being negative down here, so the answer would be 0. But because this is absolute value, instead of being negative, the absolute value graph would put this back up here being positive, and so we would have this would have some positive area here. So what we'd have to do is just use area of a triangle to calculate these out. Looks like width is 2, height is 3. We know area of a triangle is base times height divided by 2. And so here you get 3. So the area of this one would be 3. Area of this one would be 3. So the answer would be 3 plus 3 or 6. All right, last type of problems you might see if you're given some of these integrals, again, just using integral properties. Evaluate these other ones using the ones given. This first one you can see looks a lot like the one here. It's just that the limits are switched around. So remember, if you do that and switch them, you get the same thing but the opposite. And so the answer here would be 2. This next one, big thing you got to notice, they're the same. Anytime the same, you're not finding any area, it'd be 0. This next one looks a lot, again, like this one, just that the negative is here. But remember, negative is like a constant you could pull out. And so then it would be the same as the one up above here. So you'd get opposite of negative 2, or 2 would be the answer. The following one here, what is this one? Again, a constant here. If you pull that out, it's the same as the one here. And so you would have 4 times this integral, which we know ends up equaling 7. So you'd have 4 times 7, or 28. If you get one like this, where it's a combination of functions, again, constants can be pulled out. We also know we could separate these into separate ones. And so you could think of this one similar to this, and then take the given values and substitute, and you could figure it out. So this one would be 2 times negative 2 plus 3 times 7, and we'd get negative 4 plus 21, or 17. So ones like that you can separate out. Final one here, negative 1 to 4. This one's a little trickier to see. If we're dealing with x, we know for sure we can't use that one. How do we do this one? Well, you can kind of see -1. We do have -1. We also have 4 here. This is one where you could kind of combine those two. So if you did the integral from -1 to 1 of this, plus the integral from 1 to 4, that should be the same as the one indicated here. Kind of graphically what that would look like would be this. If we got some function here, here's -1 to 1, that this integral. The second one would be the integral from 1 to 4, so that would give us this amount. Together, that's the integral from -1 to 4. So here we would, if we add those two up, it would give us the value. So if you add -2 plus 5, the answer would be 3. All right, so that is kind of a review of some of the Riemann sum approximating integrals and integral properties.